Some of our previous chapters have focused on gas properties, and for this chapter we're going to talk about solids and liquids. And the first thing that we're going to discuss is the intermolecular forces, which we have talked about several times in this class already, and I kind of stressed to you that that's a really important topic in chemistry. So we're going to go over it again, and hopefully you've already heard it and it's already in your brain, but this way it'll give you a stronger foundation for these intermolecular forces. The first one is called dipole-dipole. Di means two, so when we say we have two poles, we're talking about a positive pole and a negative pole. So when you have a molecule that is polar, you have one side of it that is slightly positive, one side that's slightly negative. And so when this molecule gets near another molecule that's slightly positive and slightly negative, it's going to minimize the negative to negative attractions and the positive to positive attractions, and it's going to try to maximize these opposite charges. So notice that there's a slight positive and a slight negative, and so one molecule is going to be attracted to another. Now, these are slight positives and negatives, so they're not nearly as strong as ionic attractions because they are complete positives and negatives. And in fact, they're only about 1% of the strength of ionic bonds. And we've talked about with gases that we even make the assumption for the ideal gas law and some of those gas laws that we did, we had to make the assumption that they do not have any forces of attraction, even though there are some slight forces, but there's so much space between the particles that those forces of attraction are not significant. The next one is called hydrogen bonding, and this is a really specific one. So this occurs when you have hydrogen of one molecule, so let's just focus on water. So again, inter means between, so we're not talking about these bonds that are holding the water together, we're talking about the attraction between the water particles and the water molecules. And if you focus on the three most electronegative elements, so fluorine is the most electronegative of all the elements on the periodic table, oxygen is number 2, and nitrogen is number 3. So these three are going to be the most negative of the slight negatives. So this is a really strong slight negative. It's still not as much as an ionic bond. So if you had a complete negative, it's still just a slight negative, but of the slight negatives, it's really strong. And then when hydrogen is attached to either NO or F, it pulls all the electrons away from hydrogen because NO and F are pulling so hard on those electrons. And so hydrogen becomes more positive than it normally does. And so now we have this attraction between this slight positive and this slight negative. And it's kind of like an extreme dipole. So hydrogen is the most of the slight positives that you could get if it's attached to NO or F, and then oxygen, nitrogen, and fluorine are the most negative of the slight negatives. So you have three things that have to happen for this hydrogen bonding to occur. You have to have hydrogen on one molecule. On the other molecule, you have to have NO or F, and hydrogen has to be attached to NO or F as well. Now, the hydrogen bond is not that attachment, so this bond right here is not a hydrogen bond, even though it has H and O. That's a covalent bond. They're sharing electrons. So it has to still happen between two different molecules. And this is the strongest of the intermolecular forces. A lot of times you'll see this in examples of water and DNA, so you can focus on those and remember those as some good examples. And then our last type of intermolecular force for this chapter is the London dispersion forces. We usually talk about this with nonpolar molecules, but it actually exists between any molecule. And it's really just the random lopsided electrons that happen, and what happens is they basically, since they're moving around, they tend to get lopsided every once in a while, and so you end up with a slight negative on one side of the molecule just purely while those electrons are lopsided. And then as soon as they spread back out and get dispersed throughout the molecule, then you don't have that attraction anymore. But it's always happening somewhere in the beaker because you always have such a huge sample of molecules. And so it's always occurring somewhere in there, but it's a weak force of attraction, and again, it just has to do with the electrons that are randomly moving around. Numbers 4 and 5 are especially important for this chapter because we haven't talked about these. The word polarizability is exactly what it sounds like. It's the ability to become polar. And so the more electrons that you have in a compound, the more you would have a slight negative when they get lopsided. So the slight negative would be a stronger slight negative, and the same with the slight positive. So if we're comparing CCl4 to CH4, because CCl4 has so many more electrons, when they get lopsided, they're going to have a stronger slight negative, which will create a stronger attraction. So if you're trying to compare the forces of attraction between these two molecules, you can talk about the polarizability due to more electrons in the CCl4. However, I see a lot of students that try to use that as an argument for something when they can't, because there are other factors that are more significant. So you can only use that argument to compare forces of attraction if there's nothing else you can compare. So the first thing you should always check is what kind of forces of attraction do they have? Maybe one of them has hydrogen bonding, and that would trump all the other types of intermolecular forces. Or maybe one of them is on an ionic bond and the rest are covalent. Or maybe one of them is polar and the rest are nonpolar. So first you want to check all the different types of interparticle forces and compare them. And if you have nothing else to compare, so for CCl4 and CH4, they're both nonpolar, so the only forces of attraction that these would have between their molecules is going to be London dispersion. So then if you have nothing else to compare, then you can use this as an argument that if you have more electrons, then it's going to be more polar. But again, you want to talk about the intermolecular forces before you do that. And then the other one is the long string. So C7H16 is, it's a way to write, if you just had 7 carbons and then you have hydrogens all around the carbons as well. So this is going to be a long chain of 7 carbons, whereas this one, and I know you guys don't know how to draw these organic compounds, but you will at some point. And then we have, and this one is actually missing a carbon. There should be one more carbon in there. So this one is going to look like this, where you have hydrogen sticking off of all these carbons as well. So notice that the one on the left, you have a long string of carbons, and the one on the right is kind of a cluster of carbons that all of those carbons are stuck onto that central carbon. And so a long string has more dispersion because they kind of get more lopsided than a compact molecule. But again, you only want to use that if you have no other forces of attraction that you can talk about. For liquids, they kind of have some cool properties, and there's some good pictures. If you look at page 458 in your textbook, there's a good picture to show you how surface tension works. And surface tension you've probably experienced before. If you've ever done a belly flop off of a diving board, you've experienced that surface tension. You can also see it with those little bugs that can walk on water. Capillary action you learned about in biology. In fact, most of these you should have learned about in biology. But this is when water has the attractive properties to itself, which is called cohesion. And then it's also attracted to other things, which is called adhesion. And this is actually the reason why we get a meniscus. So we talk about when you're reading a glass container, and remember there's kind of a dip. It's an exaggerated dip, but you have to get eye level, and there's a dip in the water. And so the question is, where would you read it? Because both of those green lines are things that you could look at, and the answer is this one. You always want to look at the bottom of the meniscus. And the reason that there is a meniscus is because the oxygen in the glass is attracted to the hydrogen in the water, and so it kind of, that water is going to spread itself out onto the glass to try to get as close as it can to the glass, so it kind of spreads it up just a little bit and makes that little dip. Viscosity is tough because it's kind of the opposite of what I think. At least it's the resistance to flow. It is not the ability to flow. So I always remember that water has a very low viscosity, and honey has a very high viscosity. So it's the resistance to the flow. It's like the ability to not flow. Like I said, it's kind of the opposite of what you think. So the more intermolecular forces you have, the higher the viscosity, because the less likely it is to flow very well. And there's a whole bunch of pictures for this entire section in your textbook as well. The next section is about metals. So remember, metals are going to lose their electrons to a sea of valence electrons, and this is kind of just like a blanket of negative charge that links all of the positive ions together. So the electrons that they donate don't really go to a particular atom. They're not localized. They're called delocalized because they can kind of just float around from ion to ion. And it's that sea of electrons that gives metals all of their good properties, like conducting heat and electricity, that they're malleable and ductile. All of those things are because of that sea of electrons. This is a new vocab word. So alloy is when you have a mixture of metals. And most of the metals that you come in contact with in your life are actually alloys because it makes the metal stronger. Pure metals are actually pretty soft, so They don't want to make coins out of pure metals, like we always say, you know, nickels are made out of nickel, which they have some in it, but they're actually a mixture of different metals because pure nickel would scratch pretty easily. Same thing with pennies. They do have copper in them, but they also have other elements as well. And there's two types, and you can see some good pictures of these in your book as well. Substitutional is exactly what it sounds like, where you substitute one atom for another. And interstitial is when you put an atom into the spaces between other ones. So this one is replacing, and this one is putting it in the spaces between them. And the last section for today are network solids. And these are really cool topics. I think one of you is doing your honors project on network solids. These are especially strong compounds that have especially strong covalent bonds. And remember, covalent bonds are actually even stronger than ionic bonds. And we don't usually talk about that because when we talk about properties like boiling and melting and whether they dissolve in water, what we're really comparing is ionic to intermolecular forces. Because when you boil water, you don't break apart water into hydrogen gas and oxygen gas. You're actually separating the intermolecular forces, the hydrogen bonds between the water particles to get water vapor. And so what we're comparing there would be, we'd be comparing the ionic bonds to the intermolecular forces between water. And that's because it takes a lot of energy to actually break the bond between hydrogen and oxygen for water. So network solids are where you have multi-directional covalent bonds. And because you have all of these really strong attractions, they have kind of really cool properties. So diamond is, first of all, what you need to know about network solids are what they are. So these are solids that have multi-directional covalent bonds, and those strong attractions give them special properties. And then you also just want to know some examples of them. So a lot of times on the AP exam, I see multiple choice questions where they give you a list of compounds and it asks you several questions about it, like which one has sp3 hybridization and which one has resonance and which one has a triple bond. And one of them usually is which one is a network solid. So you just want to be familiar with these common examples so you can recognize when you see a network solid. Diamond is a famous example, and this is just carbon that's in a tetrahedral formation, but it's 3D, and there's a really good pictures of these, again, on page 471. And you've probably learned, if you've taken earth science, you've learned that diamond is the hardest substance on earth, that you can only cut a diamond with another diamond. Graphite is another one. This is what's in your pencil. Most of my students still call it lead. I'll hear students say, hey, do you have any lead? I'm out of lead. It's not lead. Lead is very toxic, and you wouldn't want to get that anywhere near your bloodstream. And if you poke yourself with your pencil, that would be toxic. So they don't use lead anymore. They use graphite. And graphite has these rings that have strong attractions, and then between the rings is a weaker attraction. And so what happens when you write with your pencil is that it kind of shaves off those rings, the layers between the rings that are weak. But the actual rings themselves don't break apart because that's a network solid. And that's why the pencil doesn't just kind of crumble off of your paper. Silica is another one. In fact, a lot of things that have silicon in them are going to be network solids, so watch out for that as an example. Like sand and glass, they all are made up of some kind of silicon compound. Ceramics, and then semiconductors as well. So, like I said, just be familiar with some of these examples. And that's it for today.